last type of induction inequality questions that I'm going to do is ones involving factorial. So this one, prove that n factorial is greater than or equal to 2 to the power of n for all natural numbers bigger than 4. That factorial, what does it mean? It means multiplied by all the natural numbers down to 1. So 4 factorial is 4 by 3 by 2 by 1. 5 factorial, 5 by 4 by 3 by 2 by 1. 10 factorial, 10 by 9 by 8 by 7 by 6 by 5 by 4 by 3 by 2 by 1. There is a button on your calculator on the sharp one there above the 4 to do it. Okay, so that's just refreshing what that actually is. We would have encountered it in probability. So step 1 is the same as ever. It is P4 that I'm kicking off with here. So show P4 is true. So that would be 4 factorial is greater than or equal to 2 to the power of 4. 4 factorial, so 4 by 3 is 12, by 2 is 24, by 1 is 24. Is greater than or equal to 2 to the power of 4 is 16. Is 24 greater than or equal to 16? Yes, it is. Therefore, P4 is true. First step done. Second one, assume PK is true. So PK would be K factorial is greater than or equal to 2 to the power of K. Step 3, prove P, the K plus 1. So that would be K plus 1 factorial is greater than or equal to 2 to the power of K plus 1. Now, as with all the inequality ones, I can't take the same step I do in the other induction questions of subbing in for K factorial here, because it's not an equation, it's an inequality. But I am going to try and link these in some way. So I'm going to try and get K factorial here instead of K plus 1 factorial. So if we just return to what factorial means, if this, say, was 7 factorial, it would be 7 by 6 by 5 by 4 by 3 by 2 by 1. So let's say this was 7 factorial and this was 6 factorial. Another way of writing this would be 7 times 6 factorial. So like K plus 1 factorial means K plus 1 times K minus 1 times K minus 2 times K minus 3 all the way down to 1. So I can rewrite this as K multiplied by, what am I saying? Sorry, K plus 1 multiplied by K factorial. Okay, so this means K plus 1 times K minus 1 times K minus 2 times K minus 3 all the way down to 1. And then this is K times K minus 1 times K minus 2. So once you have that in, they're the same thing. But writing it this way means I can link these easier. So this one here is just rewriting this. So the right-hand side is going to be the same. It's going to be greater than or equal to 2 to the K plus 1. So this is my to prove. And this is what I know to be true. So I want this to look like this. So like in other examples, I'm going to take this, but I'm going to multiply both sides by something to make it look like this. Okay, so I want the left-hand sides of these to be the same. So I'm going to multiply both sides of this by K plus 1. All right, so from PK, and then you can maybe multiplying by K plus 1. You can just tell them that that's what you're doing. So K plus 1 times K factorial is greater than or equal to, multiply this side by K plus 1 as well. and that is assumed to be true. Okay, so a couple of tricky things there. One, the kind of rewriting the pk plus 1 step so that I isolate a k factorial, and then going back to my assumption step, and to make it look like this, multiplying both sides by k plus 1. All right, now it's a similar logic to what I've applied in all of these inequality ones. So this is less than this. I'm trying to prove this is less than this. So if this is less than this, it must in turn be less than this. So you can nearly bring this one in down here. I'm going to carry on the inequality, but then just look at this bit. Okay, so true if, and I've got k plus 1 times 2 to the k is greater than or equal to 2 to the k plus 1. Right, first thing I'm going to do here is whenever we've had 2 to the k plus 1 or something like this in these inequality ones, we've split it up using one of our rules of indices. So rewrite this as 2 to the k multiplied by 2 to the 1. Okay, so you see, even though there is kind of slight differences between the, there is kind of commonalities, and we always do that. We've done that in lots of different induction questions. Now you'll notice that both sides you've got them multiplied by 2 to the k. So you can just divide both sides by 2 to the k, and you're left with k plus 1 is greater than or equal to 2. Bring the 1 over, it becomes minus, so you get k is greater than or equal to 1. Okay, so this bit here is true if k is greater than or equal to 1, which means the overall statement, because we're only trying to do numbers bigger than or equal to 4, must also be true. Okay, so, and the logic of that I kind of talk through at the kind of tail end of a previous video. You can have a look at that. Okay, I think it's the second induction one. So from here though, we can just, so therefore Pn is true for all numbers greater than or equal to 4 and just natural numbers. All right, so that's that one done. I just want to very quickly do another one, just because there's something which comes up, which will come up in the question you're doing in your book, which can throw people a little bit. So it's another factorial one. So just prove that n plus 1 factorial is greater than or equal to 2 to the power of n minus 1. And this is just all natural numbers. Okay, so they don't say n is greater than or equal to. They just say 4 natural numbers. So you can assume this is n greater than or equal to 1. That's where the natural numbers start. Don't forget, they start with 1, they don't start with 0. Step 1, show P1 is true. So it is 1 here. So that would be 1 plus 1 factorial is greater than or equal to 2 to the power of 1 minus 1. The 1 plus 1 factorial is 2 factorial, which is 2 multiplied by 1, which is 2. 1 minus 1 is 0. 2 to the power of 0 is 1. Is 2 greater than or equal to 1? Yes, it is. Therefore, P1 is true. Second step, assume PK is true. So k plus 1 factorial is greater than or equal to 2 to the k minus 1. 3, prove p to the k plus 1. So this is going to be on the left hand side k plus 1 plus 1. So it's going to be k plus 2 factorial is greater than or equal to, so I'm subbing k plus 1 in for n. So k plus 1 minus 1 1 minus 1 is 0. So it is just 2k then. All right, so same as the last one. I'm going to rewrite this so that the left-hand side looks a little bit more like this. Basically, so I find a k plus 1 factorial in it. And k plus 2 factorial is the same thing as k plus 2 multiplied by k plus 1 factorial. And that's greater than or equal to, not doing it into the right-hand side for now. All right, so that's my to prove. And then it's from PK that I'm going to get my next step. I want the left-hand side of PK to look like this. So I need to multiply it by k plus 2. If you multiply the left-hand side of this by k plus 2, you need to do the same to the right-hand side. So k plus 2 on 2 to the k minus 1. All right, and then you can say there that you're multiplying by k plus 2. It'll be clear to them, but just if you want to tie that up for them. Grand. All right, so now the kind of, so again, that's our to prove. That's my assumed true. You don't have to put those in. Again, the kind of putting them in helps me certainly get the next step right anyway. So this is true. This is less than this. I'm trying to prove this is less than the same thing. Okay, so this is less than this. So if this is less than this, it must in turn be less than this. Okay, so 2 to the k must be less than this, or just flipping it then the other way around. That is true if k plus 2 on 2 to the k minus 1 is greater than or equal to 2 to the k. All right, so just as in the last one when I had k plus 1, or whenever I have kind of something like that here, I'm going to split that up. Don't be thrown off by the fact that it's a minus 1. So k plus 2 times 2 to the k times 2 to the minus 1 is greater than or equal to 2 to the k. I've got a 2 to the k on both sides, so I can just cancel those. Now, one of the reasons I wanted to do this example is if you cancel that 2 to the k, because we tend to talk about it in terms of cancelling, it's very tempting to put a 0 there, but if you cancel that, you are leaving 1. Okay, so remember, what another way of talking about cancelling is to say you are dividing both sides by 2 to the power of k. 2 to the power of k divided by 2 to the power of k is 1. Anything divided by itself is 1. The reason we often say cancelling and don't worry about this 1 is if you divide the left-hand side by 1 there, by 2 to the k there, you're leaving a multiplied by 1. Multiplying by 1 doesn't do anything, so we tend to just not bother writing it. Okay, so like I said, that comes up in the question you're going to do in the book. Don't let that throw you off. So what else have I got? I've got k plus 2. 2 to the minus 1, negative power is 1 over. So that's 1 over 2 to the power of 1, or just 1 over 2. So multiply both sides by 2 to get rid of the half. So that will just leave you a k plus 2 on the left-hand side and 2 on the right-hand side. Bring the 2 over, it becomes minus. 2 minus 2 is 0. So k is greater than or equal to 0. So this is true if k is greater than or equal to 0. I'm only trying to prove it for natural numbers, so numbers greater than or equal to 1. So it's done. Okay, so therefore Pn is true for all natural numbers. So you can put in the n greater than or equal to 1 there, but you don't have to, because that's just what natural numbers are. That's where they start.